Hello, here's a few practice exam questions in astronomy and cosmology. Kicking off question 1, part A. Explain what is meant by a white dwarf when describing the evolution of a star. Okay, so we can say that a white dwarf is the core of a red giant. The core of a red giant. And let's give a little bit more. Sometimes you can get away just with that if they're just wanting 1 mark for this, but they are saying describing the evolution of a star. So let's say white dwarf is the core of a red giant revealed at the end of the red giant's life, when it sheds its outer layers. I mean, you could even go, if you were going to go nuts, then you could say that's forming a planetary nebula or something like that. But I think that will do. Chances are you can just say it's the core of a red giant. That's what a white dwarf is. 1, part B. Antares is a red giant and one of the brightest stars in the night sky. Yep, parallax angle for this star is 0.0059 arc seconds. Calculate its distance in light years from us, and they've given us the conversion from parsecs to light years because they want the distance in light years, and of course parallax is all to do with parsecs. So yeah, let's remind ourselves of our parallax then. So if we've got some star sitting at a distance of 1 parsec, so that would be 1 parsec. This is the sun here, so that's the sun. This is the Earth, because it's going at different extremes around the sun. So that is 1 astronomical unit, but it doesn't really matter. That's a fixed distance that we're looking at. We've got our angle there. Let's call that P. If you've got a star which is much further away, we've now got a different triangle, but with certain similarities, as in the base of the triangle, this 1 astronomical unit has stayed exactly the same. So we can exploit the fact, okay, we've now got another P there, let's call that P prime. We can exploit the fact that these are small angles. So small angles mean that tan of P is roughly equal to P for these small angles. This is our small angle approximation. So in terms of this then, we can say that, so for red P, then that is going to be the same as tan P, which is our opposite over adjacent. So that is our base here divided by the 1 parsec. So we're saying that the angle is 1 over d for the distance there. So that's what we're doing when we're working out parallax. We're taking this small angle approximation and just applying it to these nearly similar triangles. I mean, they're not similar triangles, but at least they've got one side in common. So I can't even remember what I'm trying to work out now. Right, so we've given us the angle here in arc seconds. So if we want to get the distance in parsecs of this, then our distance is going to be 1 divided by 0.0059. That is going to give us the distance in parsecs. So that comes out at, what's this, nearly 170, so 169.49 parsecs. Now we just need to get this into light years, so we just need to multiply by 3.26, and then that is going to give us 552.5, which is 550 light years to 2 significant figures. So I don't know where I'm going to write that. Let's just write it up here. 550 light years to significant figures. So yeah, it's worth keeping in mind. Okay, you don't need to go through all of this. They probably even give you the formula for these things, but it's useful to have an understanding of what's going on with parallax. C, Sirius B is a white dwarf. Yep. In comparison with Sirius B, Antares has 12 times greater mass, 1.1 times 10 to the 5 times greater radius. And then they've given us surface temperatures. Intensity I of EM radiation emitted from the surface of a star is related to its temperature T in Kelvin according to this. Okay, right, fine. Explain what is meant by intensity. So this is the power emitted per unit area. That is our intensity. Calculate the ratio mean density of one divided by the other. Okay, so our density is mass over volume, which means it's going to be proportional to mass divided by r cubed. So if we're doing density Antares divided by density of Sirius B, then that means, have they done them all relative anyway? 12 times greater mass, and all right, so we don't even care. They've set the density, all of the parameters for Sirius B to be equal to 1, so we don't even have to worry about that. This is going to be equal to then 12 for the mass multiplier divided by the cube of the radius multiplier. So this is going to be a pretty small number by the time we've got to it. So still going to need the calculator for 1.1 cubed. Actually 11 cubed we could probably deal with, but then we've still got the difficulty of dividing. I'm saying all this while I'm tapping it in. So we've got 9.016, and then that'd be times 10 to the minus 15. So 9.0 times 10 to the minus 15, two significant figures. So that's that first one. Then the total power emitted in ratio on these. Right, they've given this for the intensity. So this is power emitted per unit area. So we need to do t to the 4 multiplied by r squared in order to get our power emitted. So yeah, we need t to the 4 is our intensity. Multiply that by r squared being the area. That gives us the power. So that's what we're working out. So, but this time is not all relative because they've actually given us some temperatures. So that means we're going to have 4300 to the power of 4 divided by 25000 to the power of 4. That's our ratio of temperatures, or intensities in this way, temperatures to the power of 4. And then we've got the radius is just that straight multiplier then. So we then have to multiply by 1.1 times 10 to the 5, which we are then squaring. So that's quite a lot to tap into the calculator. And that is giving 1.06 times 10 to the 7, which is 1.1 times 10 to the 7 to two significant figures. So yeah, although it's much cooler, the much greater surface area means that you get much more power emitted from the larger but cooler star. So that's why you've got stars like Betelgeuse, that have got really high intensity. That's why they're low magnitude stars, even though they're cool, even though they're at the cool end of the spectral classification, they're still really luminous because of the huge surface area that they've got. And we've got a similar thing going on here. Okay, this is a red giant rather than a red supergiant, but it's still very bright for that reason. Right, so that's question 1. Question 2, state Hubble's law. Hubble's law, right, recessional speed of galaxies. So it's worth saying of galaxies or of objects outside of the Milky Way. You need to make sure that you make it clear that you know that this is not to do with objects within inside our galaxy. So recessional speed of galaxies is a good way to go about it. Is proportional to their distance from us, to distance from Earth. Okay. So, because yeah, if they're outside of our galaxy, then you're getting actual change in recessional speed based on the expansion of the universe rather than any kind of motion that might be happening inside our galaxy. Part B, redshift of a specific spectral line in the spectrum of a galaxy can be used to determine its recessional velocity. Yes. Fractional change Z in the wavelength of a spectral line is given by this. Okay. Where c is the speed of light in a vacuum. So that's just our Doppler equation. Table shows data for some of our closest galaxies. The distance of the galaxy from the Earth is d. Okay, right. So they've just given us those values. Complete the table by determining V and D for Messier 109. Right, this is going to be pretty straightforward then. So V is just going to be, well, it's Z times C. So 3.38 times 10 to the minus 3. So don't forget these bits up here. They've got lots of these numbers kicking around. So that was our Z multiplied by C, 3 times 10 to the 8. That gives 1014 times 10 to the 3, because we want to get it into these 10 to the 3 units here. So we've got 1014. So, well, let's say 1010. So that is that one. That's meters per second. And then we've got what D is. So, well, all of these have got to be in proportion. This is what we've said in Hubble's law. So let's just take the first one in the list then. I mean, we could take any of them. I'm just going to go with the first one off the list. So if we take this number, divide it by 336, and then multiply it by 1.5, as in taking that number and that number, then we're going to get our new value of D, because they all have to be in proportion, which gives, in this case, 4.53. Now, we get slightly different numbers depending on which row we use of data out of all of this. So it doesn't have to be exactly 4.53, but yeah, that's what we end up getting if we use the top row. So that was good. There's got to be more to this question than that, I would expect. Yes, here we go. So we've now got, they've plotted out the data. So use this to determine the age of the universe in years, and they've given us the number of seconds in a year. Right, these are one of the ones that's really difficult. I can't really do this properly on the screen, but you're going to want to draw your best fit line going through these. Work out the gradient of this line, because the gradient is equal to our Hubble constant. So that's what we want to work out. So I'm just going to go off of a triangle based on this point at the top. So here we've got, well, I've made it a big blob now, but it's about, what, 670 times 10 to the 3. 670 times 10 to the 3. That's our change in Y. Change in X is 3 times 10 to the 23. So that is giving 223. Just this one you can do in your head, which is quite fine, quite okay. Times 10 to the 20 on this, that's seconds to the minus 1. So we want then that the age of the universe, 1/h0, is going to turn it into seconds, as we can see from the units. So that gives 4.48 times 10 to the 17 seconds. Then we need to divide by this to get it in years. So let's divide that by 3.16 times 10 to the 7. And that is going to give, what have we got, 1.42 times 10 to the 10 years, which is what, 14 billion years, which is what we'd expect. So let's just put that down as 1.4 times 10 to the 10 years to 2 significant figures, or even 2 significant figures might be pushing it. So that is that part. One last bit on here. One piece of observational evidence for the Big Bang is that galaxies are receding from each other. Explain what is meant by the Big Bang and suggest 2 other observations that support the Big Bang model of the universe. Now, you don't have to go into great detail on these. You're just getting a mark for each statement, so you don't need a lot. So as simple as saying that the Big Bang is the creation of the universe, that will be enough to get you a mark. Yeah, so that is the Big Bang, is the creation of the universe. 2 other observations that support the Big Bang model of the universe. So we can say the cosmic microwave background radiation. I'll just put BR for background radiation. Cosmic microwave background radiation, obviously write it out in full, at 2.7 Kelvin. So that is something else which supports it. It doesn't say here you have to say why it supports it. We just have to say that there are 2 other observations. So we don't have to go into detail about that. If they're going to ask you to go into detail about the cosmic microwave background radiation, they'll actually say that. They'll ask you to describe why it supports the Big Bang. So let's not get carried away here again. And then we could say, let's go for primordial levels of concentrations, amounts, primordial amounts, that's what I'm looking for, of helium, lithium. So those sort of observations that have been made of how much helium and lithium are around. Again, this is supporting the Big Bang model of the universe. So that's two options that you can pick up on there. But yeah, in these sort of ones, this would have been a 3 marker for that, 3 marks. So you're just doing statement, 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 1 mark, 2 mark, 3 mark. So they have other types of questions, don't they, in the astronomy ones, where they ask you to flesh it out a little bit more. We'll probably come across some of those soon. All right, question 3. Oh, we're on here with Sirius again. Sirius A, Sirius B, binary stars in our galaxy, distance of 8.6 light years from the sun. Sirius B is a white dwarf, diameter 12 kilometers. So you're really seeing how small these white dwarfs are, even though they've got this large mass. Calculate the density of Sirius B. So our density is our mass over volume. Mass is easy enough, 2 times 10 to the 30. Our volume, then we've got to do 4/3 pi r cubed. So 4/3 pi, and then r. So remember, this is the diameter they've given here. So 6,000 meters cubed. 6,000 meters cubed. Okay, so we're going to have, I'm just going to simplify this a little bit. So that'd be a 6/4, so a 3/2 pi. Then we've got a 1/6 cubed. And then we've got a 10 to the 9 and a 10 to the 30. So that'd be times 10 to the 21 out of all of that. Right, so now I feel quite happy to sort of tap all of this in. Less likely to make a mistake on the calculator with fewer numbers. So that's 2.2 times 10 to the 18 kilograms per meter cubed. Okie dokie. The mass of the sun is the same as Sirius B. Sun has a diameter of this, so a lot more than the 12 kilometers that we got for Sirius B. Calculate the ratio of gravitational field strengths on these. So our gravitational field strength we know is proportional to 1/r squared. It's got that inverse square to it. So in this case, we're going to have the radius of the sun squared will go on the top of the fraction, and the radius of Sirius B will go on the bottom of the fraction because they're both inverses. So this is going to just be, where was the radius of the sun? So 0.7 times 10 to the 9 all squared divided by 6,000 squared, which comes out as 1.36 times 10 to the 10. 1.36 times 10 to the 10. So 1.4 times 10 to the 10. Two significant figures. Right, so far so good. Calculate the parallax angle in arc seconds for Sirius B. Right, we've already had a look at some of this, but here we go. 1 parsec is that distance. So we've got, they haven't given us seconds in a year. Didn't we have that earlier on? I don't know, I'll just type it all into the calculator. It doesn't really matter. So 8.6 light years equals, so that'd be 8.6 times speed of light times 60 times 60 times 24, as in I'm doing seconds in a year, times 365 and a quarter, 0.25. So let's just tap all of that in, because this is giving us this bit here is giving us the distance in 1 light year, and then we've got 8.6 light years, so that's going to give us the total distance. So I'm getting a light year into meters out of this, or at least 8.6 light years into meters, which comes out 8.14 times 10 to the 16 meters. So now we can divide that by our meters in a parsec over here, 3.1 times 10 to the 16, and that gives us the parsecs. So the 10 to the 16s cancel. That is giving us 2.63 parsecs. Okay, so but we want the parallax angle. Okay, and then the parallax angle, and this is what we were talking about earlier on, is 1 over the distance in parsecs. So it's 1 over 2.63, which equals 1 over 2.63. And of course, this is in arc seconds. So we stick that in and we get 0.38 arc seconds. Right, so that's that one. Sirius A is moving towards the Earth at a relative velocity of this 7,600 meters per second. Calculate the percentage change. Percentage change is what we want here in the wavelength of a spectral line observed from this star compared with an identical spectral line observed in the laboratory. Now, they actually gave us that. We did this earlier on, didn't we? They put the formula up, didn't they, for it? So we had a fractional change. The fractional change is just V over C. That is our fractional change from our Doppler shift. So that's fractional change. So we need to get the fractional change and then multiply it by 100. So the percentage change is going to be equal to V, which is 7600, divided by speed of light 3 times 10 to the 8, then multiply by 100. So what is that going to be giving us? That is giving 2.53 times 10 to the minus 3. So 2.5 times 10 to the minus 3 in two significant figures. Yeah, we had that earlier on. They do give it in the formula booklet. You quite often get it as a delta lambda over lambda. That is our fractional change, is V over C. So sometimes they'll write it as they did previously and say, I think that's what they called Z, wouldn't it? I think. So yeah, that as fractional change, or you've got this as fractional change. It's the same thing. So that was fine. Last part. A student suggests that the distance of Sirius A can be calculated using Hubble's law and the speed given in D. Discuss whether this suggestion is correct or incorrect. Well, no, we spoke about this in the previous question, actually, with the definition of Hubble's law. So we need to say that no, Hubble's law applies to objects outside of the Milky Way, not to objects within our own galaxy, outside of our galaxy. So yeah, so that sums up that last bit. Right, I think I'll leave those at 3 for now. I think you might start dragging on a bit if I go on to another question, but they were 3 nice questions to get us going.